MAP4C 5.1 Trends in Data. What we're going to do is investigate linear, quadratic, and exponential relations in the form of an equation, a graph, and a table of values. So as an equation, y is equal to mx plus b is the form of a linear relation. So m is the slope, which is rise over run, and we can talk about the difference between these two points as a slope. If we call this x1, y1, and those are subscripts to give it the name, just indicating that it is the first point. The second point, which we could refer to as x subscript 2, y subscript 2, to indicate that it's the second point. And we will use the rise over run form whenever we can see the actual squares on the graph and we have a one-to-one relationship for our scale. Here we have one square, or one grid space, represents half of a unit. So counting the squares is not really helpful in calculating the slope. We have to use our point slope form. So y2 minus y1 is just another way of calculating the rise. In this case, our rise would be 20. In our run, which is our horizontal displacement, we have 3 minus 1, which is 2. So b is the y-intercept, the next component of this equation. And here we can see by inspection that the y-intercept, where the line crosses the y-axis, is 40. So this is the graph. It's a straight line. And the table of values, whenever we plot our points or write these in a table, what we can do is, if we have a consistent interval for x, then what we can do is look at the intervals for y, the difference between adjacent points. So here we have a difference of 10 between each of these points. You could do 50 minus 40, 60 minus 50 is 10, 70 minus 60 is 10, and so on. And if this is a consistent set of first differences, then we know that this is coming from a linear relationship. Quadratic relations. As an equation, we can express a quadratic relation in standard form, factored form, or vertex form. What do they have in common? Each of these terms are degree 2 polynomials. Notice that x squared is the highest power of x. And it's not obvious in factored form, but if you were to expand and simplify, we would have x times x, which is x squared. So the degree is also 2 in this form. And then lastly, vertex form, x minus h squared, this is just a repeated factor. This base x minus h is x minus h times x minus h. So we would have a degree 2 polynomial for the same reason. An example of an equation, this is y is equal to 5x squared minus 8x plus 12. So we know that this is a quadratic relationship because it's degree 2. Which form is this in? Standard form. Now the graph can open up like this in a U shape, and some important components are the following. It's symmetrical about some axes, and we have x-intercepts that can be important in application questions, as well as y-intercepts, usually for initial position. And the vertex is commonly an important point for optimization. Next, in a table of values, what we need to do is, if we have consistent spacing with our x interval, then we can look at the first differences of the y values. Remember, that's subtracting adjacent points and finding the difference between the two. When we do our first differences, we don't see a pattern, but taking second differences, so then we look at the differences of the first differences. And it's constant. It's always the same. And whenever the second differences are constant, then we have a quadratic relationship. Exponential relations. So as an equation, y is equal to ab to the power x, where a is the initial value and b is the growth factor. So this equation, y is equal to 10 times 2 to the power x, what we can say is that it's an exponential equation because it has a variable as an exponent. Here is where we see our variable. And what characteristics of this exponential relationship we can determine just based on this equation? The initial value is 10, so its y-intercept would be 10. It's the starting position. And 2 to the power x means that the value that is initially given will be doubling. So that's our growth factor. So that growth factor b is what is responsible for determining whether we have exponential growth or exponential decay. And for values like b is greater than 1, we can expect to see exponential growth. And this makes sense because this power, b to the power x, whenever we have repeated multiplication, if your number is greater than 1 and you keep multiplying by that number, you'd expect a larger value once you exceed 1. For exponential decay, here it says whenever b is between 0 and 1. And we can think of this like percentage growth. If you needed to find out 13% of a number, for example, you use the decimal equivalent number. 0.13 is equivalent to 13%, percent meaning per 100. So you would repeatedly multiply by that value, and the value overall would be decreasing. So that's an indication as to when you would have exponential growth versus exponential decay. A curve with a horizontal asymptote. Now this horizontal asymptote is this line that it's approaching but not actually crossing. So you can imagine here, if this was taking half of the value at each point, you'd always have half of the value remaining and never actually touch the x-axis. Next, as a table of values, what we're going to do is check to see that we have consistent values and spacing for x. And when we investigate our y values, we need to take the ratio. Now, a ratio means a fraction of y2 minus y1, just adjacent points and dividing them. 2 divided by 1 is 2, 4 divided by 2 is 2, and 8 divided by 4 is 2, and so on. If the ratios are constant, the table of values represent an exponential relation.